From the distant reaches of our solar system, two worlds loom, Neptune and Uranus, the ice giants, cloaked in azure storms and swirling methane clouds. Yet beneath their beautiful facades lies a secret so extraordinary that it rivals the most opulent treasures of Earth. Every day, these planets experience a cascade of literal diamonds, falling from the heavens like glittering rain. This is the story of how the universe forges gemstones in the heart of a storm, and why those celestial jewels never reach a human hand. The tale begins with the elemental composition of these distant planets. While Earth's atmosphere is dominated by nitrogen and oxygen, the outer giants are rich in hydrogen, helium, and a substantial amount of methane, a simple hydrocarbon that, under the right conditions, becomes the seed of carbon crystals. Deep within the planets, pressure and temperature rise dramatically, creating an environment unlike any found on our home world. Scientists first hypothesized the possibility of diamond formation when laboratory experiments demonstrated that compressing methane to extreme pressures transforms it into solid carbon. In 2004, a team at the University of California, Berkeley, used a diamond anvil cell to squeeze methane to over 1 million atmospheres, observing the emergence of microscopic diamonds. This breakthrough hinted that the interiors of Neptune and Uranus could be natural crucibles for the same process. The next clue came from a different field, astrophysics. Observations of the planet's magnetic fields revealed that they are generated much deeper than previously thought, implying a conductive layer of exotic material. Models suggested that carbon, under pressures exceeding 1.5 million bars and temperatures of 4,000 degrees Celsius, would adopt a metallic liquid form, an ideal medium for the transport of solid carbon particles toward the surface. Computer simulations now paint a vivid picture. As methane descends, it encounters crushing forces that break its molecular bonds, freeing carbon atoms. These atoms then arrange themselves into hexagonal lattices, the very structure of a diamond. As they grow, they become denser than the surrounding fluid, beginning a slow, inexorable descent toward the planet's core, only to be thrust upward by convective currents that dominate the outer layers. But the journey does not end in the abyss. The ice giants are roiled by massive storms, winds that can exceed 2,000 kilometers per hour. These turbulent flows act like a planetary furnace, heating the interior and driving powerful updrafts. As the newly formed diamond crystals are caught in these updrafts, they are carried upward, passing through layers of supercritical water and ammonia, each layer adding to the drama of their ascent. When the diamonds finally breach the visible atmosphere, they encounter temperatures low enough for them to solidify into glittering hailstones. Imagine a storm where, instead of water droplets, the sky is peppered with translucent, sparkling gems. The rain of diamonds is not a gentle snowfall, it is a violent, high-velocity cascade that shatters upon impact, scattering micron-sized fragments across the planet's icy clouds. Spectroscopic measurements from the Voyager 2 flyby in 1989 provided indirect evidence of this phenomenon. The spacecraft detected unusual infrared signatures that matched the vibrational modes of solid carbon. While the data could not definitively prove diamond rain, it offered a tantalizing hint that the planet's atmospheres were not merely composed of gases, but also contained exotic solid particles. More recent observations from the Hubble Space Telescope and ground-based telescopes have refined these findings. By analyzing the scattering of sunlight through the planet's upper atmospheres, astronomers have identified bright, point-like reflections consistent with the presence of crystalline carbon. These reflections vary with the planet's rotation, suggesting a dynamic, ever-changing pattern of diamond precipitation. The implications of daily diamond rain extend beyond mere curiosity. In planetary formation theory, the existence of solid carbon phases influences thermal conductivity, magnetic field generation, and even the ultimate fate of the planets. Diamonds, being excellent conductors of heat, could accelerate the cooling of the interior, altering the timeline of magnetic dynamo activity and affecting the planet's evolution over billions of years. On a more speculative note, some scientists have pondered whether these diamonds could be harvested. In theory, a future probe equipped with a magnetic or electrostatic capture system might skim the upper atmosphere, collecting carbon crystals for use in deep space construction. While the technical challenges are staggering, the concept fuels the imagination of engineers dreaming of building habitats with materials forged in the heart of a planet. Yet, for all its allure, the diamond rain of Neptune and Uranus remains an inaccessible marvel. The extreme pressures, searing temperatures, and relentless storms make any direct sampling mission a near impossible undertaking with current technology. Nonetheless, each new mission, be it a flyby, an orbiter, or a sophisticated telescope, brings us a step closer to confirming the glittering truth of these alien downpours. The story of diamond rain also invites us to reconsider our relationship with Earth's own resources. While humanity mines diamonds from deep within our planet, the cosmos produces them in a perpetual, natural cycle, untouched by economics or exploitation. It is a humbling reminder that the universe harbors processes of staggering scale and beauty, far beyond the reach of our grasp. As we gaze at the distant blue worlds, their storms raging with unseen brilliance, we are reminded that the universe is a forge of wonders. The daily rain of diamonds on Neptune and Uranus is not just a scientific curiosity, it is a testament to the extraordinary alchemy that occurs when chemistry, physics, and planetary dynamics intersect. In the cold darkness of the outer solar system, gems fall like meteors, painting a picture of a cosmos where even the most precious stones are born from the fury of a storm. Beyond the glittering curtains of Carbonado, the interiors of these ice giants host a turbulent dance of supercritical fluids. As pressures climb above 1.5 million atmospheres, hydrogen and helium become metallic, conducting electricity like a colossal dynamo. This magnetic furnace fuels the fierce auroras that ripple across the poles, and it is precisely this electrical storm that lofts diamond-laden droplets from the lower mantle, hurling them into the upper atmosphere where they crystallize before their final, dazzling descent. The journey of a nascent diamond is a saga of survival. Encapsulated within a tiny sphere of liquid methane, it endures temperatures soaring beyond 2000 Kelvin as it spirals upward. Along the way, the particle collides with charged particles, acquiring a faint electric charge that guides its path along magnetic field lines. These charged diamonds can linger for weeks, suspended like luminous pearls, before gravity finally drags them back toward the planet's turbulent cloud decks. On Uranus, the tilt of the axis creates a seasonal rhythm that modulates the intensity of diamond rain. During the long winter, the reduced solar heating allows the upper atmosphere to cool, increasing the condensation rate of carbon compounds. Consequently, the planet experiences a heightened cascade of gem-laden droplets, a phenomenon that may explain subtle variations observed in its infrared emissions over the decades. These gem-filled showers are not merely a curiosity, they have profound implications for the planet's thermal evolution. Each falling diamond releases latent heat as it solidifies, acting as a microscopic furnace that redistributes energy from the deep interior toward the outer layers. Over billions of years, this process may have slowed the cooling of Neptune and Uranus, preserving their internal heat longer than models without diamond precipitation would predict. The existence of diamond rain also reshapes our understanding of exoplanetary chemistry. Many distant worlds orbiting close to their stars are classified as carbon-rich or diamond planets. By studying our own solar system's ice giants, scientists gain a laboratory for testing the equations of state that dictate whether carbon will condense as graphite, soot, or pure diamond under exotic pressures, a key to interpreting the spectra of those far-flung worlds. Future missions may finally harvest these celestial gems. A probe equipped with a high-speed, heat-shielded collector could skim the upper clouds, capturing falling diamonds before they vaporize. Such a sample would provide an unprecedented window into the deep chemistry of Neptune and Uranus, allowing laboratory analysis of material forged under conditions unattainable on Earth. In the grand tapestry of the cosmos, the notion that the most valuable stones are forged in the heart of a storm reminds us that beauty often emerges from chaos. As we gaze upon the distant, icy behemoths, we are witnessing a silent, glittering fury, an endless rain of diamonds that tells a story of creation, transformation, and the relentless power of planetary physics.